In this video I will discuss the node setting types and what their purpose is. It is recommended to watch the video about the graph editor basics. We will start with an introduction about the setting types and later discuss the actual demo implementation like the animator settings or follow settings. You can find all relevant information in the video description as well. Let's start by creating a new graph editor. One of the most important settings is the decider setting. The decider setting helps you to branch to certain other deciders or actions. It is basically there to form an AI tree for decision making. You can link other deciders in the input port list, and if you change the decider branch type from branch to isLeaf, you see that the port list changes to the leaf settings list. There you can only link action settings. If you don't like this mechanic, feel free to create your own decider via the control panel, which is also linked in the video description. Here I will set up a single decider as a root that links to two other multiple deciders, which in the end connect to action settings. As you can see, the action settings have way more information in the node inspector. We will cover that in a later section of this video. Now we add a condition to the first multiple decider in the single deciders connection list. Since the single decider only chooses one traversal path in its children, so if the first decider we add the conditioner would fail, the second one would be traversed. Condition settings are a very helpful node setting and are also very important, if not crucial, for decision making. Otherwise you would never know when to deny or validate a sub-branch. If you're wondering what's behind the debug info foldout, it's basically information about the node port connections and sometimes stores hash values. It is not recommended to tamper with the values there, otherwise you might break the graph and nodes. Now I will explain the base action settings that are shared with every custom action settings that is existing and you might create on your own. The checkbox repeat execution indicates if the action should loop or only execute for a set amount. The repeat execution amount is the number for additional execution. So 0 means that this action will execute once. Up next we have the execution delay timing. So if you have the engine running each frame, you sometimes don't want the action to execute each frame as well. This is often the case for spotting. So here you can define how often the action should execute, either instantly, every tick call of the engine, or every X millisecond or second from a certain range, and the value in that range will be picked randomly. The max stackable field indicates how often the same action setting may be present in the engine. In most cases you only want one instance of the same action that represents this setting, but sometimes you might have an effect that stacks with the same action running. Also, do you want to tell the decider if the branch failed when the max stack limit was reached, or should it succeed because the action was already present in the engine? The priority field indicates in which order the action should run alongside other actions in the same engine. The highest priority will be called first. The next checkbox indicates if the values of the engine or AI entity should be restored once the action is disposed. For some actions this setting does nothing, And if you implement your own action, you have to override the restore method and handle the values to restore on your own if you have anything to restore in the first place. You might want to dispose the action if the validation failed, or give it a few more shots until the action is disposed. I almost forgot to mention the conditions at the beginning of the setting. You have a condition on enter, which only triggers once the action setting is validated when traversing through the leaves of the decider. The condition to validate condition is called every tick of the engine and if the action would be executed, so it also depends on the execution timing. So the validation condition is called right before the run method is called of the represented action object. The disposal condition is called after the run execution of the action and indicates if the action should be disposed of the engine. Next we have the disposal timing, which is checked right before the action is run. Once the time is reached, the action will be disposed. The represent state field shows what state this action setting and the action object represents. Also, it is helpful to dispose the action from another source, such as another decider or action, or even via calling the remove state method on the AiMalgam entity mono behavior. Let's create a new state that represents this flee action setting. We can change the label of it, although now it seems like we came across a text focus bug. You can fix this by reopening the graph. As of now, it is not known what causes this bug. Reopening the graph helped, and we can change the label of this state. And if you unfold the debug info foldout, you see that we generate a label hash for the label for faster state comparisons. Once a label hash is generated, it is stored in a global string hasher dictionary. So whenever you switch back to the old label, the respective hash is also displayed. You can set in the action setting that you want to dispose this state from the AiMalgam entity once this action is done. Looking into the debug info of an action, you will find its action type supported name and hash that is used for mapping the respective engine to the setting. Now you know that no expensive reflection calls are used for finding the engine for the action. Upon successful validation of the action setting, you can dispose other states and actions, either all of them or specific ones. You can also set blocking states. When this action wants to enter the engine, it will read states that are currently active on the AiMalgam entity, or just listen to states when they enter the AiMalgam entity and dispose while this action is active. The decider settings also enables this option, and they perform it once they validate, meaning that the traversal was successful. Some deciders may have more settings than the simple ones. For example, the multiple decider offers you an option to play the settings in an async manner, meaning that not all action settings are applied all at once at the same time, but wait for the previous one to finish and either abort on a failed one or continue, or abort or continue on the same decision made or a different decision made, etc. Now a specific setting for the flee action setting is a list where you can add runtime variables. So this port list is not a base setting which is there for every custom action setting unless defined specifically. Runtime variables are scriptable objects that can temporarily store runtime objects, so they get cleared once you go back to editor mode or restart the application, but while running they can dynamically fill up objects from different scenes in one list, and you can include them in your action setting and action logic. Another Flea action specific setting is the comparer targeting setting. Its purpose is to compare and sort a list of AiMalgam entities based on the specified comparer scriptable object. In this case, we just get the last entity of the list. And to finish up the AI decision tree, you must set up a root decider. You can do that by right-clicking on a designer and click on Assign as Root. If you want to call other deciders on Unity lifecycle events, you can assign them and set it up, for example, on Start or on Awake. If your AI decision tree grows too big, you can always change the visibility option. It is also recommended to work with subgraph deciders and split your AI tree into smaller ones for better maintainability and modularity. Some conditions are special. There are conditions that need descriptors to read the data values from and check them against in order to validate or invalidate the condition. If you open up the debug info foldout, you will see the descriptor type supported name and hash to map the desired descriptor from the AiMalgam entity to this condition. Now I will explain the available node setting implementations in detail. We will start with the deciders. As already explained, the single decider only picks the first valid child, either the decider or action setting. So keep in mind to have the list in the correct order. Up next is the score decider. This one chooses the children with their highest condition result score. For action, it uses the condition to enter to read the score from, and from deciders it uses their condition field or input to read the score from. This is very interesting because you could theoretically implement a decision system that learns from its mistakes or successes, so you can adapt the score for each iteration or generation, similar to evolutionary machine learning, although the machine learning part needs to be implemented first. There are some conditions and descriptors that work together where you can read a condition result directly without having any condition logic, so you can tamper with the condition result values in the game environment yourself. Another very special decider is the subgraph decider, which links to the root decider of another node graph. With that you can modularize your graphs and decision trees and reuse them more easily, as well as keep a better maintenance and performance. Now let's get into the action setting implementations. We will start with the animator settings. As you can see, it shares the same base settings as the Flea action settings we have inspected before. This is the case for every action setting, even custom ones you implement. With the animator settings you can set parameters of an animator controller. We can define the parameter type at the top of the animator settings section and set the internal value below. Restoring values on this pose for this action causes the animator controller parameters to set to the previous values before they were tempered by the animator action object. Also, you notice there's a new field in the dispose settings section. You can dispose the animator action once the desired animation value is reached and set the approximation value for float values. Also, there's a blending settings section for float values where you can interpolate between the current and target float value for the animator parameter value. Usually though, you just stick with the animator damp time field in the action settings. But to find the correct parameter name, you should first assign the animator controller in the action settings. It is easier to select the name by a drop-down menu instead of typing it by hand and accidentally mistyping the name. A animator parameter hash will be generated. Oftentimes you don't want to set a static value to the animator controller parameters, but rather change them dynamically. For that you can check the Use External Values checkbox and select how to read or where to read the external values from. Using the Blackboard External Values Read option, you can define what Blackboard key to read from the animator engine to put it into the action object and finally in the animator controller parameter. This is a perfect example in how to use the Blackboard data injection pattern for engines and action objects. If you choose the scriptable object reader, you can simply add a RuntimeVariable to read the desired parameter value from. And in the game environment and runtime environment, you can tamper with this scriptable object and its value, in this case the float value, to apply the animator parameter and thus the animation. Sometimes the external values are not clamped right for the parameter, so you can set it up in the settings as well. If you want to keep the same ratio of the external values, you can map them from a certain input to output range. So the percentage or relation would stay correct. Make sure to have the animator set up on your entity and how it should be updated and if the root motion should be applied. In newer versions I needed to change the update mode to apply physics. Also make sure the avatar is correct. For the animator action you need the animator engine and assign the animator to it. To react to state changes, make sure to check the subscribe to any state change entity checkbox. This is present in every engine. Here you see the decision system mono behavior referencing the respective graph for this paladin fighter entity. For the humanoid entities, I have set up the agent observer descriptor, which reads the desired move force from the navmesh agent and applies the result to the Blackboard dictionary in the animator engine. Finally, the actions apply the desired movement animation to the animator controller. Let's continue with the any settings, or as I like to call them, the lazy settings. The any settings just contain a bunch of different primitive and more complex data types And if you inherit from the base any action class, it will show up in the any actions drop-down section. This is an easy way to implement your own custom action objects and logic, but it is way slower during instantiation. So preferably you should implement your own action and engine pack. This is just for quick testing. For any actions, you also need the any engine. As always, you need the respective engine for the action setting type. You can find out what required engines are needed in the side panel graph inspector within the graph editor, or if you click on required engines on the decision system mono behavior. Now let's take a look at the combat action settings. Each combat setting must represent a specific combat tool. It is helpful to add a combat descriptor where you can handle getting hit from another combat system from another AiMalgam entity. You can also set up events on hit. It is important to add a combat tool destination container and link each combat tool mono behavior in it. Then each combat tool must reference the combat tool type so that the combat action setting with its combat tool type can find the right combat tool to work with. Also, you can set up hit appliers for the combat tool so that you can implement physical impacts rather than only logical hits via code. Again, I like to remind you that all of the demo implementations are just custom implementations from the AiMalgam core. You can always add your own combat or animation or flee or follow systems, even all being done in one engine. Also note that it is not restricted on the 3D environment. You can also add AI that works in a 2D platformer game, or flying AI such as planes or birds, even racing, whatever you want. Finally, link the combat tool destination container to the combat engine. You can also set a local targets container, which is optional, or even filter targets by keys. Most of the time you use the same target destination container, the follow engine outputs, so you combat the same entity you are following from the follow system. You can set that the combat action does not validate when it cannot engage a target or does not have the required target amount to engage. Do you want to calculate the targets every run, or do you want to save the targets and only recalculate the next one once the old targets are gone? Do you want to update the resulting targets in another destination container, which is then set in the engine? Similarly to the flee, follow and spotting settings, you can set up a global runtime set variable to read the target entities from. It is important to set up a special combat procedure. They are called combat state properties, and you can define combat with several steps, for example a start phase, a shoot phase, a cooldown phase, which then need to be called in the correct order and possibly wait for certain animation events or Wait for the combat tool, or rather the weapon, to perform the action and end its phase, to then go to the next combat state property, or restart the combat state properties procedure. You can also choose from multiple combat state properties by defining special conditions for each property. Make sure to add another state property or restart the search, otherwise you get stuck, unless this is what you want. Once in the combat state property, you can set states on the target or on the entity which runs the combat system. You can also prevent new targets being calculated by checking the log current targets checkbox. Set if the tool should hit directly when this combat state property is activated, or override if the hit appliers of the combat tool should hit or not. Also, you can skip the wait and go to the next combat state property by checking the override apply next combat state property checkbox. Be careful though, in most cases you want to wait for animation events to finish and then to execute the next combat state property. Also keep in mind to synchronize the running action times and how often the animation event is called and how your animator controller handles the animation transition. So sometimes you might miss the transition by calling it too early or too late. So always keep that in mind. Let's take a quick look how the archer handles the combat. There is one for melee combat and one for shooting the bow. As you can see, we use an AND condition and also set certain states to indicate that the archer is attacking or fleeing or drawing the bow. For the bow combat action, we wait until the bow shoot animation event is emitted to then play the combat state property attack. And afterwards we go back to the draw bow combat state property once the conditions are met to do so. The combat action also allows you to link a comparer node setting to sort the targets in a specific way, for example by distance or the first one or a random one. Usually you don't need to do that, since you can blindly use the output targets of the follow system. Now let's take a look at the spotting action setting demo implementation. You don't need to call the spotting action each tick of the engine, but rather every 300 or 400 milliseconds. With that you can save some performance and simulate reaction times, similar to the real world. In the disposal settings section you can tell the action to be done if it spotted something. There are 4 different spotting mechanics you can use. Each one represents another spotting action, which inherits from the base spotting action class, all of which use the same engine. The contact spotting action type spots an entity on collision or trigger enter. The raker spotting type spots an entity if it is directly in front of the ray being casted. You can define the min-max distance the ray can cast, which layer is allowed to spot the entity, and if it can spot an entity that is behind other objects. Also you can define if the spotted entity must be between a certain amount of colliders. The view cone spotting type is a bit more sophisticated. There an entity can be spotted even if it is not directly in front of the spotter or hosting entity. You can define how big the view cone angle is and if it should respect other colliders to block the direct sight. For view cone and distance-based spotting, you either must define runtime set variables or a target destination container in the engine for spotting. This is because the spotting action must compare the existing entities to spot against the view cone and spot direction. You can set up different view cone types, one being the one angle for all sides we just saw, the other one being split into horizontal and vertical angles, and the last one is split into 4 sides, being the topmost area to spot, the leftmost, the bottommost, and the rightmost cone area to spot an entity. All from the local perspective of the spotter, of course. You can see that options are getting hidden if they are not used by the current spotting type. Note that you can set up a spot delay and a spot loss delay. By default, the spot entity is spotted instantly and never lost or never forgotten. Also, you can set if the spot was done silently, like in the stealth mode, or in a loud manner where the spot descriptor of the victim or the spotted is being triggered that the entity has now been spotted. Let's take a look at the spotting engine. As you can see, you can emit events once an entity has been spotted or once an entity's spot has been lost, depending on your spot delay and spot loss delay settings. Usually you want to set up a spot descriptor and fill its entities up, where you can also filter certain entities to keys and use them later on in targeting for following or combat systems. Most of the times this is also the best way to make another decision so your entity can react to the spotted one if you set this up in your AI decision tree. With that, you don't have to iterate to the tree each frame and just wait until spotting is done. In the spot descriptor you can also define new colliders that can be spotted by other entities. For example, you can build a big giant that can also be spotted by its arms or legs or gear, so you have a more realistic spotting scenario in the game. As you saw in the settings, you can define a contact spotting type. For that you need to add contact collectors to the spotting engine, where it can read from what entity was collided or triggered with. Below you see the current spotted entities and the potential spotted entities. The potential spotted entities are the entities which will be turned into the current spotted entities once the spot delay time has run out you have set up. If it is done instantly, you will never see any entity in the potential list, or at least they will flash and that's it. You can define the caster where to spot from. Most of the time you want this around the head area, otherwise it will be the hosting entity. Make sure to face the spot caster's direction in the local Z direction of your hosting entity, so it is not shifted in the wrong angle, like 90 degrees or 180 degrees or whatever the caster and the parents are facing and what your expected result is. In some engines you can display some visual effects for debugging, which are only visible in the scene editor view and not in the game window view. You can enable this either in the settings for every entity that is running the action or just on the engine. You can also set how long the visual effects should stay until they will be refreshed. If you call the action not every frame, it is useful to set a longer time. Otherwise, you might want to stick with a very low number. Here you can see that the hide spots actually use a trigger spot collector. So even the seemingly lifeless entities are actually AI entities. You can also define reactions to certain spotted entities depending on the conditions you set up, where you can link a certain spotted entity to another destination container and set states on the caster or on the spotted entity as well. The first valid reaction to spotted setting will be chosen. Every setting after that will be ignored for the current spotting and processing entity. That means that other entities in the same spotting action may have another reaction container. You can set to remove the state if the entity's spot is lost, or lock the state even though another reaction container was found. Now let's take a look at the follow action settings. You can find the follow specific section below the base settings. There's yet another dispose setting for the follow actions, which tells the action to dispose once the destination is reached in a certain distance. There are different ways to follow a destination, either by tailing the target or choosing a random point independent of any target, simply looking at a target without moving, or trying to flank a target constantly. The restore values checkbox only restores values when using the just look at follow type. There the angular speed of the navmesh engine will be restored, and if the navmesh engine was stopped before. You can also blend between the current destination and the target destination if you want. This is especially useful if you use transform apply as the follow method. To choose which target to follow, you need to specify a compare node setting. To save performance, you can cache the target until the condition to pick a new target is validated, or until the current target is lost. You can also output the current target and use it for combat systems. If you have set up key to destination containers in your engine, you can also filter targets. There are different ways to perform the movement, either by the navmesh agent or free of any ground restrictions, although there currently is no collision avoidance in the air movement space. You can clamp the min-max height when not using the navmesh agent as a follow method. You can simulate random walks or search patterns with the random point follow type. For that you need to define the min-max distance area based on the central area transform in your follow engine, and define where the next point should spawn. Also you can set up if the spawn point can be behind the entity or only in front of the entity or always to the right. You can also create a shift so the entity will always move in a circular pattern. In the just look at target follow type, you can override the navmesh angular turn and restore it if you want. Also you can clamp the relative local angular rotation so that the target, for example, only moves in the Y direction locally, that is, not globally. You can take a look at the tower defense example for that. You can also force the NavMesh agent to stop to only look at the target. Choosing the simple flank target as the follow type, you can refresh the flank angle and flank distance or keep it consistently for the action's lifetime. Similar to the spotting settings, you can also visualize the movement pattern of the follow action settings. This is also possible in the flee action settings. Now I will show you the follow engine, where you can define the follow movement by setting up the NavMesh agent, rigid body or transform. You don't need to fill up every field unless the actions require so. The central area transform, by default the entity itself, can also define another transform to restrict the entity to not move outside of it, as you have seen in the random settings. Here you see the entity destinations to keys container for the follow engine. The flee engine has a very similar setup, since it's also all about movement. You can define an output destination container for the followed targets, which will be filled by checking the update targets in Blackboard checkbox in the action settings. Let's take a look how the paladins use the flank settings. As you can see, they are not just simply staring at each other and fighting, but they constantly move around. This is because the other target moves around, tries to flank the current target, and also because the flank angle and distance changes every 4 to 6 seconds. In the other examples, we just use the tail target follow action settings. You can also see that in the hide and seek example, the targets never leave the area, even though it is open and there is a NavMesh surface on it. The last action setting we cover is the flee action setting. It is very similar to the follow action setting. Instead of following the target, the flee action tries to predict the chase direction and choose a random point from the chase direction and the current fleeing entity. Also, what's different to the follow action setting is that you can define a new random flee point and don't need to start a new flee action for that. You can also define the key to destination filters similar to the action setting, and also if you want to cache a chaser until it gets lost, or the condition to pick a new chaser is validated, or the general condition for a chaser to run from in the first place. Let's take a look how the editor visual effects look like for fleeing and following. Well, to see the results, the entity has to flee first, so my mistake. Let's take a look at another one then. Let's decrease the lifetime of the follow line. And now you can see and debug where the entity wants to go. Always make sure that you're in the scene window, since this is not visible in the game window. Let's take a look where the chaser wants to go. And I have made another mistake again. We displayed the spotting visual effects, not the follow visual effects. Here they are. Since we opened a graph while the game was running and we had a decision system selected, you can see some nodes being rendered in green. Those are the currently active actions. But we are here to display the visual effects for every entity that runs this action, not only the engine. Let's see if the other C car also displays the path now. And as you can see, it does, even though we have not touched its engine. But its line lifetime is also set too long. Notice that the settings still remain even though we exited play mode. This is because we changed scriptable object files and not mono behaviors. With the exception of the engines, of course. I mean the node settings we changed. Now that we are done with the action settings, I'll show some important condition settings you might want to use. You can group multiple conditions together, not just use one single condition for an input port. The AND condition container and OR condition container are just the use case for that. The AND condition container only validates if every listed condition is also validated, and the OR condition container already validates if any condition in its list validates. It also ignores each condition after that to save performance. The random condition is also a nice condition. It validates or invalidates by the given chance. Then you have the condition result reader, which reads a condition result from the descriptor when found on the AiMalgam entity. With condition grouping you can create giant clusters of condition, which can simulate some complex decision making. Another very helpful condition is the state condition. Here you can match the condition states against the AiMalgam entity states, either by saying that none must match to validate, or that at least one state must be found in the AiMalgam entity that matches the state found in this list, or match all, even match all with the same amount, so no more or less on the entity, and also if you want to check the hierarchy of a state, since you can also define parents for states and build a hierarchy with that. If you want to negate existing condition and you don't want to rebuild the same cluster, you can simply drag the condition inverter and assign the desired condition to negate its validation. The condition score will also be inverted. For example, 0.9 will be 0.1 after running through the condition inverter. The other node settings we already covered on the surface are self-explanatory. The most complex one were the deciders, the actions, well, by far the actions, and the conditions. That's it for this video. I hope I could give you some helpful insights about the existing node settings and how to make use of them. Remember that you can create your own AI implementations by using the code creator panel if none of the demo implementations do the job for your game. Happy AI creation!